So as application of stationary waves, we'll be looking at vibration in strings, vibration in pipes. In pipes or tubes, we have two, the open pipe and then closed pipe. Vibration in strings is what the string instrument, guitar, violin, name them, the principle upon which they work. Vibration in pipes or tubes, trumpet, wind instrument, trumpet, trombone, name them, saxophone, okay, those wind instruments. That is what they also apply. So we are beginning with vibration in strength. Vibration in strength. So vibration now, before we look at vibration in strength, you see, progressive wave, any wave with a particular wavelength or and frequency can form it. For a progressive wave, any wave with any particular wavelength and frequency, let me write this for you. So any wave with a particular wavelength, any wave of a particular, or let me put it, any frequency and wavelength, any frequency and wavelength of a wave forms a progressive wave. But a stationary wave or standing wave is formed by a particular, or instead of particular, let's use peculiar wavelength and frequency. What I'm saying here is that for formation of progressive wave, any ordinary wavelength and frequency of a wave can form a progressive wave. Okay, any ordinary wavelength and frequency of a wave can form a progressive wave. But to form a stationary wave, you need a particular or peculiar or special wavelength and frequency of wave to form this. That is to say that you don't expect just any wavelength and frequency of a wave to form a stationary wave. But for stationary wave, you need a special or peculiar wavelength and then frequency to form. So it means that any stationary wave has its peculiar wavelength and frequency in forming a stationary wave. So vibration in strings. We have a string. This is a string of length L. Because we are forming a stationary wave, there should be boundary or barrier at both ends. So this is barrier 1. Barrier 2. Now, if the string, so practically this is similar to, you see the guitar strings. The guitar strings, let me have a improvise something for a proper understanding. So take this cable to be the length of the string. Okay, my two hands represent the barrier or the boundary at both ends. Now, when I plug the middle of the string, I create a wave around it. But because there are boundary at both ends, an incident wave created, and then there's reflection. The incident wave hits the boundary and then reflects, creating that characteristic stationary or standing wave. Is that okay? So an application of this is that, you see, if you have seen the guitar before, the strings which are consistently plugged to create the sound, okay, is fixed between two metals ends. Okay, so this is an application of the guitar string is an application of vibration in strings. So this string has a length L. Now, when the string is disturbed or plugged, you see there are a series of stationary waves that can be created. Okay, so if you have, I don't know if any of you has listened to the sound from guitar string before. When their guitarists are playing and then they plug the guitar string, you hear the sound. That the sound created, there is that continuity. The sound that just doesn't end. That no, but when you plug the guitar string, it creates that continuous sound. That continuity of sound you hear is as a result of the different stationary waves that is created. These different stationary waves are what we also call as the notes, N-O-T-E-S. So once you plug it once, you hear that continuous sound. And that continuous sound tells you that there is that series of stationary waves that are created or notes. So let me give you some notes. Then we go into the theory of vibration in strings properly. So a vibration or disturbance of the string creates a multiple stationary waves around the string. Stationary waves or notes, N-O-T-E-S, around the string. And each of these nodes, stationary waves, or node has its peculiar each of these stationary or wave or nodes has its peculiar wavelength and frequency. Don't forget, I said stationary waves are formed with a particular wavelength and frequency. So each of the nodes or stationary waves created around the string has its own wavelength and frequency. So let's look at the first possible stationary wave. The first possible stationary wave that is created when the string vibrates. Okay, so information of this. Don't forget that we said stationary wave is also two progressive waves traveling from opposite directions and then superimposing or interfering like this to create. So in drawing the possible stationary waves or nodes, we use a progressive wave. Now, the first possible stationary wave or nodes that will be formed, because there is a barrier at this end, must start from a node and end with within another node or at another node because there's a barrier here. So once there's a barrier, we start from a node and end with a node. So the first possible stationary wave that will be formed will start from here and then end here. So it's as if the second barrier is here. So this becomes the incident. It hits the barrier and then reflects to create the stationary wave. So the first possible stationary wave that will be created when the medium is disturbed will look like this. Start from a node and within another node, and then reflect to create this. This is the first possible stationary wave. The first stationary wave or what we call as nodes created when the string is disturbed. So why are we talking about this? And I said earlier that we are talking about this because if we have a string L and with boundary at both ends, when you cause a vibration of the string or you disturb it, it creates that continuous sound. One disturbance can create sound like brrrr. That continuity is as a result of a lot of stationary waves or nodes. If it is just one stationary wave, you just hear one stop sound, then it ends. But for strings, when you disturb it, you hear continuous sound, telling you that the sound that is created has multiple stationary waves. So the first possible sound or stationary wave that is created is like this. It starts from a node and within another node. Please, class, are you okay?
Yes, please.
Okay. So this is the first possible stationary wave or notes that will be formed in vibration in strength. Earlier, I also said that stationary waves are formed with a particular wavelength and frequency. So we are going to look for that particular wavelength and frequency which forms this stationary wave. Not any wavelength or frequency of wave can form a stationary wave. Stationary waves are formed with a particular wavelength and frequency. So when you draw the possible stationary waves, then you look for that special wavelength and frequency which will form each one of them. So this becomes the first possible node or stationary wave. Please, the nodes are also known as the stationary waves. Okay. So this string has a length L. From node, this special fundamental or beginning node or stationary wave formed from node to node. We want the wavelength of this. What will be the wavelength from a node to another node? What is the wavelength from node to node? Yes, we went through this. So yes, what is the wavelength from node to another node? Josephine.
Mr. Bia.
What is the wavelength from node to node? Oh, Josephine.
Mr. Bia.
Yes.
I'm coming.
Josephine, can you hear me?
Yes, please.
I said, what's the wavelength from node to node? You don't know.
This
Abia Adoma, what is the wavelength from node to node? Abia Adoma. Ah, Abia, are you there? Oh yeah.
Mr. Bia, please half of the wavelength.
Half of the wavelength. Yes, we did this. Josephine, we did this.
Yes.
You can't forget this basics, please. So the wavelength of this wave from node to node is equal to half lambda. Okay. What it means is that this L length of the string is equal to the wavelength of the wave, which is half lambda. Now, stationary waves are formed with a particular wavelength and frequency. Okay, so let's look for that particular wavelength. And please give me a minute, I'm coming in. So this L length of the string is equal to a wavelength of half lambda. Therefore, when we make lambda the subject, we have 2L over 1. I earlier said that stationary waves are formed with a particular wavelength and frequency. So this is that particular wavelength which forms this note. So we call this as lambda 1, which is the fundamental wavelength. Because this is a fundamental note, this is the foundation, the beginning, fundamental note or stationary wave. This wavelength is equal to, it's also known as the fundamental wavelength. So this becomes that special wavelength which forms this stationary wave. Immaculate. Hello,
Yes,
Immaculate.
sir.
Ah, okay.
Yes.
All right. So that's it. So we found that special wavelength and frequency which will form these notes. What about that special wave frequency? This is the wavelength. What about that particular or special frequency which will form this? Now, when the medium is disturbed, the wave or the waveform, okay, travels with the velocity of sound in air. So because speed of sound in air, V, is given by frequency times wavelength, we pick the frequency or we determine the fundamental frequency from this relation. F is equal to V over lambda, meaning that the frequency is equal to the velocity of sound in air over that wavelength, particular wavelength, which forms this, which is 2L. 2L. And so this F also becomes F1 or the fundamental frequency. Fundamental frequency. Okay, so fundamental wavelength, fundamental frequency, because this is the first or the foundational stationary wave or note. So we found that particular wavelength which formed this stationary wave, and we've also found that particular frequency which will form this. The fundamental frequency is also known as the first harmonic. First harmonic. Later on, you understand what we mean by harmonic. So either the fundamental frequency or the first harmonic. Please, if there is any question, quickly ask before we continue. Is there any question? Hello, is there any question? Okay, so if there is no question, let's look at the second possible stationary wave that will be formed. I said one disturbance of the medium creates continuous sound. Creates a continuous sound. So the second possible stationary wave that will be formed is this. The second overrides the first. So because there are boundaries. We start from a node. There's the first. There's a node here. So it means the boundary must be here. So the incident will be this, hits and then reflects to create this. So this becomes the second possible stationary wave. So let's draw it. This is just to guide us be able to generate the possible nodes or stationary waves. So first one hits the boundary and then reflect. We are not that the length of the string is still the same, L, the same length. So this becomes the second node. The second node or stationary wave. L length of the string is equal. What's the wavelength of this? Calculate the wavelength of this note for me. Josephine, calculate the wavelength of this note for me.
Sylvia, please, lambda.
So this is from half lambda, another half lambda. So 2 times half lambda. So L is equal to 2 lambda over 2. And I'm doing this for a reason. If you recall, the first one, L was equal to 2 lambda over 1. Okay, even though 2 lambda over 2 is still lambda, but we want to later create a general relation. So it means that lambda 2 would be equal to 2L on 2. L on 2. This becomes that particular wavelength which forms this. So this is the second. We saw the fundamental wavelength. So the second wavelength which forms this. I want you to help me determine F2 from V over lambda. What do you think will be F2? What will be F2? Yes. What will be F2? Oh, yeah.
Two V over 2L.
Come again.
2 V over 2L.
So 2. So V, when we substitute lambda here, 2, lambda 2 here, we have V over 2L then times 2. Now F2. What did we get for F1? What did we get for F1?
V on 2L.
So F2 is also 2 times F1 because this is equal to this. So F2 is equal to 2 times F1. So this is the frequency of the second harmonic. Frequency of the second harmonic. We'll do it for the third stationary wave and create a general relation. Okay, so this is the second wavelength, and then F2 is the frequency of the second harmonic or second frequency. I said this V is equal to the velocity of sound in air. L is equal to the length of the string. Take note. Okay. The third possible stationary wave that will be formed from a node to a node. So first one, second, this will be the third. So it means the barrier the same length. Therefore, the same length L, but the stationary wave for the third harmonic would have to be 1, 2, so reflect to form this. All this is happening from one vibration, one disturbance of the medium. Okay, so we have L equal to Ishra. What will be the wavelength of this node? Ishra, what will be the wavelength of this node? The third node. I don't know if you were around when we were doing this, Ishra. Ishra, were you around? Hello, Ishra. Were you around when we were doing this? Okay. Oye, what will be the wavelength?
Please pray unto
Oye, speak up, speak up.
pray unto lambda
3.
and 2.
Okay, so we have this is half, half, half. So we have 3 times half lambda. Okay, node to node, node to node. So half, half, another half. So this is equal to 3 lambda on 2. Therefore, lambda 3 is equal to 2L on 3. So this becomes that particular wavelength which will form this. Then we look for, I want you to determine the frequency of the third harmonic for me, F3. How do we determine F3? F3. Yes, what is F3?
3
Any of,
times F1.
pardon?
Three.
Josephine, your line is breaking.
Please, 3 times F1.
So 3 times F1. Let's go systematic. So this will be V over lambda 3. So we have V over 2L times 3. And either 3V on 2L, or because V on 2L is the first one, 3 on F1. Okay. Now, what will be the nth wavelength? When you're asked to determine the wavelength and the frequency of maybe the 80th note or stationary wave. Listen, I said the 80th note or stationary wave. You can't be drawing 80 of this. Hey, when will you finish? 1, 2, 3, 4, 80, then no. There should be a way out. When you are given higher notes and to determine the wavelength and then the frequency of the notes. How do we do it? This is how we do it. You see, the first note, each wavelength, lambda 1, we have 2L on 1, meaning 2 times the length of the string. Each frequency, we had F1 to be equal to V on 2L. Then the second note, lambda 2, we had 2L on 2. Each frequency F2, we had 2 times F1. The third wavelength, we had 2L on 3. Each frequency F3, 3 times F1. So there's a pattern, meaning for the nth wavelength or nth note, the wavelength for the nth note will be equal to 2L on n. And Fn would also be n times F1. So if I'm asked to find the wavelength of the 80th note, it's simply 2L over 80. And F80 would also be equal to 80 times F1. So the n relation would help you, okay, or will stop you from drawing a lot of notes before finding the wavelength to determine the frequency and then the wavelength. Please, is that understood?
Yes.
So this is what we mean by what goes into vibration in strengths. Determining that special wavelength and then determining that special frequency. Now, for strengths, from what we've gone through, it means that for strengths, for vibration in strengths, the harmonics, which are the frequencies, are both odd and even. Don't forget F1 F1, we had F1. The second note, we had 2F1. The third harmonic, we had 3F1. We had the fourth harmonic, 4F1. Down to NF, F1. Meaning we had 1, 2, 3, 4, 5, on and on. So it means that the harmonics for vibration in strings are both odd and even. Odd, even, odd, even, odd, on and on. So it's a mixture of both odd and even harmonics. Okay. Practically what this means is that whenever this string instrument is example guitar is played in church, the sound frequency of sound you hear, the sound moves, each sound has its own frequency. So whatever you hear, whenever a string instrument, guitar, violin, harp, and all that is being played, is that you hear frequency within a mixture of frequencies, both even and odd. So example, if assuming F1 is 100 hertz, the next sound you hear will be 200 hertz, 300, 400, 500, on and on and on. Each frequency is a mixture of both odd and even. And that brings quality or harmonics into the sound we hear from guitar or string instruments. Later on, we'll look at other instruments and you see how its frequency also go, and as a result affects the quality of sound you hear when such instruments is played. Okay. Please, is there any question? So these are the fundamentals which you need to understand. Now, this frequency of sounds depends on some factors. Now, velocity of sound in velocity of transverse wave in strength depends on some factors. I'll create a theory and then bring it to a practical situation where you would be able to connect better. Now, velocity of a transverse wave. Don't forget, a wave can be transverse or longitudinal. Velocity of a transverse wave in strength depend on some factors. Okay. Whenever you want to create sound with strength, the velocity of sound you hear, okay, and this kind of sound or wave created on strings is an example of transverse wave. The reason for which it is being termed as velocity of transverse wave in strings depends on some factors. When some factors changes, it can also affect the quality of what you hear. A typical example of one of the factors is the tension in the string. One. So velocity of sound, velocity of transverse wave in strings depends on one, the tension in the string. Two, it also depends on the length L of the string. So the L as considered earlier, length of the string. And the third one is that it also depends on the linear density. Linear density mu of the string. So the tension T, length L, then the linear density mu. How are these factors applied in string instruments? If you've been so observant in your church, or if you play any musical instrument, those of you who join regimental, do I have any of you here? Any of you joining the regimental group? Do I have any one of you? Ishra, are you a member of Reggie?
No, please.
Josephine, what about you? Anoye?
No, please.
Oh, okay. I'm sure you've also been observing instrumentalists in your church. You see, whenever on Sundays, for the instrumentalists to use the church guitar, for instance, they need to go to church early and tune the guitar. What it's actually meant by tuning is that they need to ensure that there's a particular tension within the string. So they'll go early, then tie it. There's a knob where you need to hold and tie the string. Then they will vibrate it, or yes, cause a vibration or strike it and see if it produces very good sound. Because they need to go early and do that, because it takes time to set to get the required sound which it must produce. And the frequency of the sound you hear goes with a particular tension. So they need to go early. So if you stay close to a church, early Sundays, they will be disturbing. I don't know if you've observed that. As they do that, they want to give it that particular tension, which will give them a very good sound. Okay, because the velocity and the frequency of the sound depends on the tension in the string. Two, guitar strings vary in length. So if you've been observant again, you realize that the length of the guitar strings vary like this. Usually 5 strings. So there's a knob here. There's also a knob here. On and on and on. This variation in the length of the string gives it a different sound frequency. Apart from variation in the length, it also comes with the thickness. The 5 strings vary in thickness or the diameter. Okay, some of them very, very small, some of them large. So all the 5 strings vary. These changes in the strings are put in place so as to give you different sounds or frequencies, so that you can actually jam with whatever sound that is produced. Okay, so velocity of transverse wave in strength depends on these three factors by this equation. By this equation, V is equal to T over mu. The length will come in later. But velocity of sound in string is equal to this. V is equal to T over mu, where V is equal to velocity of sound in air. T is equal to the tension. Please don't make the mistake to see this as temperature. It's tension. Then mu is equal to the linear density later on. The length would also come in. Now linear density mu is equal to mass per unit length. Mass per unit length. I said mass per unit length. So when L is equal to 1 meter, then mu becomes m over 1, which is simply m. So if the length of the string is equal to 1 meter, the linear density is just equal to the mass of the string. So here to m is equal to mass of the string. So if we are talking about 1 meter length of string, then linear density is equal to m. So when you see V expressed as square root of T over m, then it means that we are considering just a meter, 1 meter length of a string. And so the linear density is just equal to the mass of the string. Please, is that okay?
Yes, please.
All right. Now, so mu is equal to m over L, and tension is also the same as weight. Tension is also equal to mass times acceleration due to gravity. There are situations where information will be given, there will be the need to calculate for T and all that. So take note of this relations as well. We'll be using it in our question solving. Okay, so if velocity of sound depends on this, velocity of sound depends on this, then we can also relate, because we can relate frequencies to velocities, the n frequency is equal to n times f1. And this is also equal to n times f1 is v over 2l. Okay, so if velocity of sound in string is equal to this, then the n frequency can also be n times we are substituting v, T over mu on 2L. So we can say that the end frequency Fn can also be n over 2L times T over mu. If n is equal to 1, F it will simply be equal to 1 over 2L times T on linear density. So from here we can relate that the frequency of sound in strings so if we are looking at the harmonics, first harmonic F1 will be this. If we are factoring in these factors on which the velocity and frequency of sound depend, then F1 will be equal to this. F2 would also be, we said F2 is 2 times F1. And so it will also be 2 times 1 on 2L times T on mu. So 1 on L times T on mu. F3 on and on and on. So generally, we can also say that then the harmonics, the frequency of sounds in string, okay, frequency of sound in strings, F is inversely proportional to the length of the string. You all have 1 over L. But F will be the inversely proportional to the length when or at constant T and mu. For F to be inversely proportional to L, T, the tension and the linear density must be constant. So at constant T and mu. Okay. The relation we can derive from here is that for 2 different lengths, there will be 2 different frequencies. If F is inversely proportional to this, so F1 will be 1 on L1, F2 will be inversely 1 on L2. Therefore, we can say that F1 over F2 would be equal to L2 on L1. So this equation can be used for some calculations that at different lengths, when L1 has its own frequency F1, then when we vary the length, we must be able to determine the frequency. From what we have, we can also say that F is directly proportional to the square root of the tension. But this will also work for at constant L and mu. So for F to be inversely proportional to the tension, then the length and then the length of the string and the linear density must be constant. What we can also derive is that F1 is directly proportional to T1 F2 would also be directly proportional to T2. So F1 over F2 would also be equal to square root of T1 on T2. So different frequency, different tension would give you, all right? So this is the second law, which we can derive. F is inversely proportional to L. Then the second one is that the second one is that frequency of sound in string is also directly proportional to the tension. Then the third one is this. From here, F is inversely proportional to 1 on mu at constant L and T. At constant L and T. The equation we can also derive here is that F1 over F2 must be equal to square root of mu2 over mu1. Please, is that understood?
Yeah.
Hello?
Is it the L? Is it the whole length of the string or the length from one note to the other?
Is the length, L is the length of the string, the whole length of the string. So when all that we are saying is that when you vary the length of the string, it will produce different frequencies. You see, practically, this explains the reason why, you see, when guitarists are playing, we have the whole length of the string. But because they know that the sound they create, the frequency of the sound they create has something to do with the length of the string, when they are playing, they wouldn't just be striking the string, bing, 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 because when you do that, you just hear one sound, bing, 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 bing. No. So when they are playing, they have their other hand, okay, in constant touch with the string. While they are doing this, what they are doing is that they are creating a barrier within the whole line just to vary the length of the string. So if they are playing and then they touch the string, they are creating a barrier. So it will shorten the string. Okay, shortening the string would create different notes or stationary wave. When the stationary wave changes, it will also change the frequency. So when they play and then they do that, it creates harmony in the sound you hear. That is why they do that. Other than that, they will just be striking, bing, 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 bing. But when you do that, you only hear one frequency of sound. But when they play and they are in constant touch with the string, they vary the sound or frequency of sound you hear. That is why they do that. Any other question? Okay, let's solve a problem. Let's solve a question. I'm reading. A stretched string of length 12.4 centimeter. A stretched string. A stretched string. I'm coming. So from today, when you go to church, be observing your guitarist. And then those who play the violin. Watch them very well. Next time we'll talk about wind instruments, where you'll be observing the keyboardists and then the trumpeters. So a stretched string of length, the length is 12.4. A stretched string of length 12.4 centimeter, which is plugged at the middle, vibrates with a fundamental frequency of 512 hertz. So it vibrates with a fundamental frequency of 512 hertz. What will be the frequency? What will be the frequency if the length is changed to 16.2 centimeters? So what will be the frequency if the length is changed to 16.2 centimeters? So when the length is 12.4, we have a frequency of 512 hertz. If the length is increased to 16.2, what will be the frequency? So L1, F1, L2, okay? And for this to hold, the tension and the linear density must be constant. So do it and then get back to me. Who is true? Ajua, what have you had? Immaculate. Immaculate.
Yes, sir.
What have you had?
Sir, please, I'm not done.
Yeah, I'm not done. Inshira. Inshira. And Inshira, have you gone to sleep? Josephine,
Yes, please.
what have you had?
391.9 hertz.
Leave your answer in 1 dp.
391.9 hertz.
Oye,
Mr. Yeah, please, the same thing.
Ekuya,
So please the same.
Ajua,
Yeah, please, I the same.
Immaculate. Inshira,
Yes, I got the same. Please, I got the same thing.
Inshira. Where is Inshira? Okay, so the answer is 391.9. Question 2. A stretched spring under a tension of 20 Newton. A stretched spring under a tension of 20 Newton vibrates at a frequency of 500 hertz when plugged at the middle. Calculate the frequency with which the same string vibrates. Calculate the frequency with which the same string vibrates if the tension is changed to 30 Newton. Calculate the frequency with which the same string vibrates if the tension is changed to 30 Newton.
Miss Xavier,
Hello.
please can you hit the first part of the question?
Okay. So a stretched string under a tension of 20 Newton, a stretched string under a tension of 20 Newton vibrates at a frequency of 500 hertz. 500 hertz. When plugged at the middle, calculate the frequency with which the same string vibrates if the tension is changed to 30 Newton. Okay. So when the tension is 20, we have frequency of 500. When the tension is changed to 30, what will be the frequency? That's the question.